Let's continue to practice the technique of separation of variables. In this video, we will solve examples 2 through 5. So first of all, example 2, we have the differential equation dy dx equals cosine of x divided by y squared. Now this was originally written as y prime, but I like to write dy over dx for these problems because it helps me to think of the separation of variables here. So we can just write dy dx as y prime of x. The notation is equivalent. So first we separate the variables. I'm going to multiply both sides by y squared, and then also multiply both sides by dx, and that will separate the variables. So y squared dy equals cosine of x dx. So I've successfully separated the variables. I am ready to integrate. So we have the integral of y squared, that is y cubed divided by 3. That equals the antiderivative of cosine, which is positive sine, and we add the plus c only on the x side of the equation. Now, we want to solve for y, so I'm going to multiply both sides by 3. So y cubed equals sine of x, 3 sine of x, and I could write 3 times c if I wanted to, but c is just an arbitrary constant. So 3 times c, that's just another arbitrary constant. So instead of mixing up different constants here, I'm just going to call this c. It's just some arbitrary constant. It's not really the same c as what we had in the previous line, but it's still just an arbitrary constant. Finally, to solve for y, we will take the cubed root. So y equals the cubed root of 3 sine of x plus c. Or we could also write this as sine of x plus c, 3 sine of x plus c, to the 1/3 power. Notice here that the plus c stays inside the parentheses. I'm not just tacking on a plus c outside here. The plus c has to stay inside the parentheses. When I take the cubed root, I have to take the cubed root of both sides. So I take the cubed root here of the entire expression 3 sine of x plus c. So here's the general solution for this differential equation. This slope field actually looks really, really neat, and the solutions are pretty crazy. So let's take a look at this in Desmos. So here's our Desmos slope field plotter, and we are looking at the differential equation cosine of x divided by y squared. So there's the slope field, and we found that the general solution here is y equals 3 times sine of x plus c all raised to the 1/3 power. And let's add a value for c here. So there is a specific solution. These actually look, doesn't that look wild, this wavy behavior of the solution function? And if we change the value of the constant c here, we're going to get different looking solutions that are all particular solutions to the differential equation. So one of the solutions looks like that. Some of the other solutions are a bit less interesting. They just kind of look a little bit sinusoidal there. But we get these very interesting different graphs, and all of these are particular solutions to the differential equation. Take a look at example 3. We want to solve this initial value problem. We have a separable differential equation, and we have an initial condition. So we're going to find the particular solution that satisfies this initial condition. So our differential equation is dy dx equals negative x divided by y, and the initial condition, y of 4 equals 3. 4 is the x value here, 3 is the y value. So let's solve the differential equation using separation of variables. I'm going to multiply both sides by y, and I have y times dy equals negative x dx. I have separated the variables. All the y's on one side, all the x's on the other. Now I can integrate. The antiderivative of y is y squared divided by 2, and the antiderivative of negative x is negative x squared divided by 2, and we add the plus c to this side. I want to solve now for y. So I'm going to multiply first both sides by 2, and 2 times y squared over 2 is just y squared, and this equals 2 times negative x squared over 2, negative x squared, and then we have 2 times c. 2 times c is just another arbitrary constant. So instead of using 2c, let's just call this c again. So I could continue to solve for y. I could take the square root of both sides. We'd have plus or minus. But for this one, I'm going to write the general solution as x squared plus y squared equals c. Does this equation look at all familiar? This is the equation of a circle centered at the origin with the radius of the square root of c. So when we solve this initial value problem, the answer that we'll get is the equation for a circle. Let's go ahead and use this initial condition now to find the constant value of c. So we know that when x equals 4, y equals 3. So 4 squared plus 3 squared equals c. And maybe you recognize this as a 3, 4, 5 right triangle. 4 squared is 16, 3 squared is 9. That's equal to c. And 16 plus 9 is 25, so c equals 25. So the particular solution here, the final answer, we have x squared plus y squared equals 25. This is a circle centered at the origin with a radius of 5. Let's see what this looks like in Desmos. So our differential equation is negative x divided by y. There's the slope field. And we can tell, even just looking at the slope field, very clearly the solutions here will be circles. So the general solution that we found, x squared plus y squared equals some constant c. And let's add different values for c. C has to be greater than or equal to 0 here for this to work. So we see that we get these different circles. These are all particular solutions. Now we want the particular solution passing through the point 4, 3. And we found that in order to get that particular solution, we need to have c equal to 25. So we have a radius here of 5, the square root of 25. And here, x squared plus y squared equals 25. There is the particular solution that satisfies the differential equation. Let's solve example 4. And I phrase this a little bit differently just so that we're comfortable with phrasing the problems in slightly different ways. We want to find the function f of x, we can really think of this as y, such that f prime equals x times f of x minus x. And we have an initial condition here, f of 0 equals 2. So this is another initial value problem, and we will solve it using separation of variables. So the differential equation that we have f prime of x equals x times f of x minus x, and f of 0 equals 2. Let's translate this to the terms that we're a bit more comfortable with. Let's let y equal f of x. So f prime is just dy dx or y prime. So we can write dy dx equals x times y minus x, and y of 0 equals 2. So this looks a little bit more like what we're used to dealing with. We want to solve this differential equation using separation of variables. But is it separable? Do I have a function of x times a function of y? It doesn't really look like it from this expression. I have something with x's and y's and subtracting x. So do you see a way that we can take this and write it as a function of x times a function of y? How about we factor an x? We have an x times both these terms, so we could write this as x times y minus 1. And now I have a function of x times a function of y. Yes, this is separable, and I can proceed with separation of variables. So I'm going to divide both sides by y minus 1, 1 over y minus 1 dy, and multiply both sides by dx, x dx. I did that kind of quickly. Make sure that you're comfortable with this step. If you need to work through a couple extra steps, go ahead and do that. But to separate the variables here, I divide both sides by this y minus 1, multiply both sides by the dx, and here's what I get after separating the variables. Now I can integrate. The integral of y minus 1, we could use u substitution if we want, but this is one of those easy substitutions. This is natural log of the absolute value of y minus 1. This equals the antiderivative of x squared divided by 2 plus c. Now in a previous example, we saw how to solve an expression like this. We had an analogous expression which was natural log of the absolute value of y equals e to the x plus c. And after solving that, we got y equals c times e to the x, and c here was any arbitrary constant. We went through some intermediate steps here where c changed to a positive constant, and then positive and negative, and then finally back to an arbitrary positive, negative, or 0 constant. But essentially the process here is going to be the same. So if I solve for y, well first let's just solve for y minus 1. Y minus 1 will be c e to the x squared divided by 2. C is an arbitrary constant for both of these. And if you look back at the example where we solved this, well, the differential equation here was y prime equals y. This was example 1b. If you look at the steps that we used to go from this expression to this expression, you could duplicate these steps for the example that we're working through right now. So the final answer here, y equals c e to the x squared over 2 plus 1. Actually, this isn't quite our final solution because we want to find the particular solution satisfying this initial condition. So let's go ahead and use that initial condition to solve for the value of c. We are told that y of 0 equals 2. That means when we plug in 0 for x, we get 2 for y. So y of 0, that would be c times e to the 0 squared over 2 plus 1. This all equals the y value of 2. Now, e to the 0 squared over 2, this is e to the 0. E to the 0 is 1. So we have c plus 1 equals 2. This tells us c equals 2 minus 1. c equals 1. So the very final answer here, the particular solution, is y equals 1 times e to the x squared divided by 2 plus 1. There is the particular solution satisfying this differential equation. And since this was phrased in terms of f, let's go ahead and rename this y to be f of x. So there's our function f satisfying this differential equation. Let's take a look at the next example. For example 5, we want to solve this differential equation. Right now it does not look separable. We don't see a function of x times a function of y, but we'll see that there is a way to rewrite this so that we do have a function of x times a function of y. So for example 5, the differential equation is dy over dx equals xy minus 3y plus 4x minus 12. Now, I want a separable differential equation in order to use separation of variables. I want something that has the form dy dx equals some function of x times a function of y. I don't have that here. I have all these different terms added or subtracted. I don't have multiplication. So what do I do here? Well, there's actually a way to factor this. This is how we can factor, and it's going to make more sense when we see the answer to go backwards to get to this step. But this can actually be factored as x minus 3 times y plus 4. Where do I get this? Well, imagine expanding this out. Think of foiling this out. We'd have x times y, xy, and then minus 3 times y, minus 3y, 4 times x, plus 4x, and then negative 3 times positive 4, negative 12. So we've just factored this expression. And now we have a function of x times a function of y. We can proceed with separation of variables. So before we could do separation of variables here, we first had to write a function of x times a function of y. Now we can proceed. So solving or separating the variables to both sides, we have 1 over y plus 4 dy equals x minus 3 dx. Now we take antiderivatives here, take the integral of both sides. Natural log of the absolute value of y plus 4 equals x squared divided by 2 minus 3x plus c. We want to solve for y, and this is really going to be similar to the previous example and to example 1b, where we have e to the power of both sides, and then we get this arbitrary constant that's just positive, and then we deal with the absolute value bars. So I'm going to just do this all in one step, and for the details of that, take a look at example 1b that we worked through. So we would get here y plus 4 equals c times e to the x squared divided by 2 minus 3x. Now the very last step is to solve for y by subtracting 4 from both sides. So we have y equals c e to the x squared divided by 2 minus 3x minus 4. And here's the general solution to this differential equation.